Okay. Okay. Are there any questions from the previous session or sessions that have popped up since we talked yesterday?
No, so far so good.
Okay. Then the purpose of this session, so yesterday, just to reiterate, we have 5 questions that we have to answer before we can, you walk in, empty instrument, your samples in hand. What steps do you need to take to be able to test your sample? First, is your hardware installed? Yes. Second, have you done your daily indentation access calibration? Yes. Third, have you defined all of your samples? Yep, we did that a couple times in a couple different ways. Fourth, is our tip to optic calibration correct? Excuse me, is our tip to optic offset correct? If not, we need to perform the calibration. We did that. And the last question was, do we have an accurate tip area function? As we all recall, the reduced modulus and hardness are both dependent upon the contact area of the indent. In an ideal Berkovich, that is a known equation, but we don't live in an ideal world. So instead, what we have to do is figure out how to describe that probe so that the tip, the contact area is correct against contact depth. In order to do so, we take the reduced modulus equation and we flip it around. And we say we know this should be 69.6. I'm going to take a bunch of indents in fused quartz at different contact depths, and I want you to solve for the contact area. So in order to do that, we had to take a bunch of indents in the fused quartz standard, which is what we covered yesterday. So we set up a load function, we set up a method, and we are now coming back to the instrument after that method has been completed. So I will have you share your instrument screen whenever you're ready.
Sorry, I thought I did already.
No problem. Okay, so normally when we come back, there's a little pop-up that says, method complete, and it tells you how many indents and how long it took. I'm guessing you just clicked OK away from that.
Yeah. Yes.
So the first thing I like to do is check how the data looks. Before I do anything else with analysis or anything, did it take the data well? Were there a lot of false indents? Were there, was there repeatability poor? Did anything weird happen during those indents that I wasn't expecting? So I would like to go to the data analysis tab. Yep, and we're in the indent. We can actually see our last indent graphed here, which is the lowest force indent at 500 micronewtons going, less than 60 nanometers into the fused quartz. So we can see some of that vibrational noise that we know is in your system. A little bit more prevalent here just because of that smaller displacement and smaller force, but otherwise it looks great. Like I'm not concerned about it, but that's what it is. And so this will graph singular graphs here, singular indents, but I want to look at all of them at the same time. So on the left-hand side, there's a series of icons. The second from the bottom is what's called the plot multiple curves. Yep. And you can go ahead and add curves. And then I'll have you add the indents from wherever you saved them yesterday.
This one?
Nope. So yesterday so go ahead and close this. And close this. And go back to method automation. Sorry, automated test here. In that top part, that's where you save that data. That's what I'm looking for.
Yes, okay.
I don't know if it lets you copy and paste. This is a very old interface. Well, it's new, but built on old. So there are all of... So I thought you saved them in the Kevin file name base folder. Is that not correct? That's what those all are?
Yes.
So these should be 200 indents, right? TAF, which was our base name, saved with the position and then the timestamp. So you can go ahead and click add. Click OK. This looks fantastic so far. Yeah, really nice, really repeatable. Oh, one outlier out of 200 indents. I'll take that. So do you want to click on that one that's obviously not supposed to be there? The one who's loading and unloading do not match. So that probably hit a piece of debris or some sort of scratch in the sample. Something happened, but position 1, number 41 is probably an outlier. While we're here, I also want to zoom in on the 0, point. So can you double click in the center of the graph? Most of our graphs, if you double click on them, you will get the axes. So let's go ahead and we're going to zoom in by unchecking auto scale. Sorry, auto scale. That's auto divisions. Recheck auto divisions, please. There we go. And then up at the top, yep. So let's do -5 to 10. And let's do -20, sorry, I'm deciding, -5 to 5. Okay, go ahead and click done. Do we notice anything about, so this is the very beginning of the curves. My question to you is, do you think that's the true 0, point of the curve, where it has 0, here? If we think about it right here, oh, go ahead.
I kind of think so. Seems like you start from here, plot starts.
Yeah, so it actually isn't. I'm gonna ask for control if that's okay.
Sure.
And the thing is that what we know is that, how do we know when we are out of contact with the sample surface? What should the force be?
2. I think there's
out of contact. When the tip is in the air, what force should we be feeling?
2 micronewton or something.
No, when it's just hanging out in air. Should it feel any force when it's hanging out in air? When it's just sitting, not in contact? No, it should be 0, right?
Yes.
The 2 micronewtons you're thinking of is the contact force it must feel in order to determine that it's in contact with the sample. Those two facts combined means that what we have here is not the real 0, point. So this is where the indent begins. And then it comes and it lifts out of contact. And what you can see here is that the force is still decreasing during the lift until this point. And then here, the lift is 0. Or excuse me, the force is truly 0, right? The force is flat. The force is no longer changing as a function of the displacement. That means that that force must be the 0 force during the lift.
Mm-hmm.
It's offset by 2 micronewtons because of that contact threshold.
Okay.
It's also offset in displacement because of that contact threshold. So truly, here we can see, it came in, it lifted out, and here is where we are finally leaving the sample surface. And that means that when we come back in, here is where we're really re-entering the sample, about right there. So this means we have to re-zero our curves. So I'm trying to demonstrate that this is necessary for every indent, even though we're only off by about -2 micronewtons and -2 nanometers. It's enough to create error in our measurements. So I'll have you go ahead and close this graph. And go ahead and open up the very first indent in this screen here.
Open the first indent.
So go to the open button on the left-hand side. Yep, open file. And then go locate your indents. And before we do anything here, actually, can you copy all of these into a folder for raw data, so that we have backup, because we're about to mess with the files. So I always like to have a raw data folder just in case. Oh, data management here.
I don't like it just all sitting there.
Yeah, I agree. Good.
Analyze.
Okay, so now let's only play around in the analyzed folder. So go ahead and open up the first indent that was taken from the analyzed folder. Okay, and I want you to do this, a similar zoom in here. So double click in the center. Right now, our goal is to re-zero all this data. We're going to start by practicing on the first indent and then apply those settings to all of the indents. So let's go from -5 to 10 on Y. And let's go from -20, -10 to +10 in X. So maybe it's a little clearer in this one. Where would you say the 0, point? Yeah, go ahead and click done here. Sorry, I'm rushing you. Thank you. Where would you say the 0, point of this should be?
Here.
Yeah, maybe even a little further back because it is still increasing here. So like right here. Okay, as long as we're all in agreement for why that should be the 0, point. Now the question is, how do we make that the 0, point? And the answer is there are 3 ways. We're only going to train on one, because if we train on all 3, people typically start to get confused and try to do part of one and part of another, and then they end up with not re-zeroed data. I left a document in the shared folder that I sent to you called Re-zeroing Data that has more information. But we're just going to train on what I think is the best way to re-zero data. So if we look on the screen, there are these force offset auto buttons and displacement offset auto buttons. Similarly, there is a displacement cutoff and a force endpoint. These are what we're going to use for the re-zeroing. Let's start with re-zeroing the force. So we have to re-zero the force first. It will become clear here in a moment why. And what we need to do is we need to pick a displacement cutoff, meaning where on this graph, where everything to the left of it should be 0 micronewtons. So if you were going to draw a vertical line to tell the system, take the data below that and make that 0 micronewtons, where would you draw that line? At what displacement?
I'm sorry, is it vertical or horizontal?
Vertical. I think I said horizontal. I meant vertical. My apologies. If you were to draw a vertical line.
But,
Yep. So what
like
displacement does that correlate to?
Like -4.
Yep. So -4 is probably safe. I usually do like -8. And the reason for that is that what we are trying to do right now is we are going to practice settings on this curve, and then we're going to take all those settings to the other curves. And there's going to be some variation a little bit in where that lands. And so we want to give it a little bit of wiggle room. So I know that I'm pretty confident that everything like behind -8 will always be 0, that the variation won't be that large. So go ahead and let's choose our displacement cutoff to then be -8. The force endpoint is similar in that it correlates to the force at which we draw a horizontal line to use the data below to fit. However, it's not as intuitive. It uses, I think, a Lorentzian fit. It's either Lorentzian or Hertzian. I need to go back and reread the document where it basically finds this inflection point. So it fits, you know, a curve here, fits a curve here, and it assumes this is 0. That is why the force offset has to be done first. So for the force endpoint, so where we choose to draw that line, it's a little bit less intuitive, a little bit more gray. The rule of thumb is that it has to be larger than your contact threshold. So it has to be bigger than here, but not so large that you can't get a linear fit. So generally I find 10 micronewtons which is right where we are, is usually a pretty good number for the fuse court standard. These numbers are going to change depending on your sample, because your sample will determine how, you know, if it's a really soft sample, this displacement offset is going to be much larger. If it's a very hard sample, it might not have a displacement, you know, change at all. All right, so we have our displacement cutoff set to -8, and I want our force endpoint to be -10, or +10, excuse me. So I want to go ahead and update that value here.
So can you repeat it?
Yep, so I think the what part of it do you want repeated? Should I start from the beginning or?
No. You just say place something.
Right, so we've input our displacement cutoff to be -8. Now we need to determine and enter our force endpoint, which I think should be 10.
Next step.
So enter that force endpoint to be 10 micronewtons. And do you understand why I'm picking 10 micronewtons, where that came from?
Is where the chop to here?
It's where we're
No.
chopping here. And I picked that number because it's above our contact threshold, but small enough that it limits the data points so that we don't over-constrain the fit.
Okay.
Okay. So now that we have these settings, we can use the auto buttons. So the force offset, and then we click auto here to 0 this force using the displacement cutoff as the setting. And then similarly for the force endpoint that we have set, you click auto here to do the displacement offset. And that should have re-zeroed it. However, we are a trust but verify kind of people, us scientists. So go ahead and double click in the center. And let's zoom back in on that 0 point. So similar values, -5 to 10 and -5 to 5. So that to me is a much better 0 point.
Mm-hmm.
So, okay, we know two things right now. We know these settings work well to re-zero this curve, and we know that this curve overlaps well with the other curves. That means that these settings should be used for all of them, right? Because I don't want to have to open up everyone, zoom in, click settings, click auto. That would take a long time for 200 indents. So instead, under the hamburger menu on the left-hand side is, gosh, I think it's under file. It's either file or analysis. Sorry, under the hamburger menu, there was file as an option. Yep, go ahead and click file. And there is what is it? Multiple file re-zero offsets, the second from the bottom. Good. And you can see here it's imported your settings, which is what we want. So, okay, we know that these settings were good for this curve, so we're going to go ahead and click OK. And then you're going to select all of your data. Click Add. And then click OK. And now it's going to re-zero. This will take a minute or two, and the software might appear to freeze. It's one of those things that Windows changed. It used to just be a nice little, if you're old enough, if you remember, used to just be a little hourglass that would say, you know, it's processing something. Now it will often say not responding when it's doing something like this in the background, when it's doing like a large batch analysis. So if you see that in the progress panel, it'll say progress not responding here. It is just working in the background, and it will come back in just a second.
Okay.
Oh, yeah, Nicole.
Yeah, I have a question like we are doing this offset to get a perfect curve starting at 0, 0, right?
Correct.
Now, when we do that reduced modulus calculation, we take at the slope of the retraction when the tip is retracting, right?
Correct.
That time, this offset, if we don't do, will not affect the results, right?
It will. It absolutely will. And I actually have data to demonstrate it. But yes, I mean, if you think about it, we're shifting the entire graph, right? It's not that we're just shifting the indent. It's that if this spot is 2 nanometers off, this spot is also 2 nanometers off, which means
Okay,
the
but the
fit.
slope will be right same.
The stiffness, yes. Yes, because the stiffness is the first derivative of that fit. And that fit also includes the fact that it's calculated at the peak displacement. So if your peak displacement is incorrect, I could see that also
Yes.
causing issues.
Yes.
So I would still argue that yes, the ReZero will definitely impact this.
Okay, thank you.
Yeah. Okay. And also your contact area, right? The contact area is determined by the x-axis, where the first derivative fit. We fit to the unload, you do the first derivative, where that first derivative crosses the displacement axes, that's your contact depth. So in addition to that, your contact depth is incorrect, which means your contact area is incorrect, which means that you then have incorrect results.
Yes, definitely. Thank you.
Yep. Okay, so again, we are a trust but verify kind of people. So now it's done re-zeroing. What do you think we should do? Yeah. Good. So overall, really nice. We still have that one outlier, so that outlier wasn't due to re-zeroing, but we can double check by zooming in a little bit more. So go ahead and double click in the center. And let's go, -5 to 5 and -5 to 5. Okay, so now that looks a lot more like a 0, 0 point for all of the curves combined to me. You can see how they all begin to actually increase in force at about this point. And here the force is now 0. So we've, it used to do this, and now we are here. So this looks a lot better to me.
Mm-hmm.
So that's step 1 for getting your tip area function, or for any data. Any data needs to be re-zeroed. Are there any questions about the re-zeroing?
Nope.
I have one.
Mm-hmm.
Like if we are not satisfied with the auto adjustment, can we do it manually too?
Yes, there is a way to do it manually. We can, I normally don't train on it again because people can get a little confused between the two, but I can show you now if you'd like me to.
Mhm.
Okay, go ahead and close this. And why don't you go ahead and open one of the raw data files to give us something real to work with. Sorry, let's open one of the raw files. So this is the analyzed files. The raw files are still not re-zeroed. That's why I want to use them for this demonstration. Okay, now go ahead and zoom in that same way that we've done. Good. We're also going to learn some shortcuts here. So go ahead and click done here. And I want you to pick where you think the 0, point should be. And click on it when you. I agree. That looks like a great 0, point to me. Do you see how the reticule is currently now there? How the reticule moved when you clicked?
It does
Yes.
move a little bit.
Well, I'm more pointing out that when you click here, you know, the reticule is there versus when you click here, the reticule updates with you, right? It moves. Because what we're going to do next, don't do it quite yet. We're going to hit Control G. And when you hit Control G, it takes wherever that reticule is and says, ah, that's 0, 0. It also does something else. It's going to open up the next indent in the same view window. So what you're going to see is after you click Control G, we're going to go from 4 to 5. I want to go back to 4 because we're going to look at it, but let's go ahead and let's re-zero this one now. So go ahead and click Control G. G is in Gus. I don't know my phenom. Okay, and now you can see all of a sudden it looks like it didn't take, right? Well, that's because we're at 5. So it's going to re-zero, open the next one, re-zero, open the next one, which is handy if you have to re-zero a lot, right? There's a trick here to get back to it. Instead of opening, you know, file open, whatever, if you click Control and then the backwards and forwards arrow keys, you can move up and down in the directory. So click Control and backwards arrow.
Backward arrow control.
You might have to click inside the graph first and then try again. So just click done here. You might just need to activate the graph. Now click Control back arrow.
Where's my arrow? Arrows.
Okay, good. Now do you see that we've gone back to 4? And your 0, 0 is now much better. It re-zeroed. So you open it, you find your 0 point, you put your reticule there, and you click Control G. That's how you manually re-zero.
Okay.
Just a lot of work for 200 indents.
So
That's the
for
batch
Control G, is that only for this one?
Correct. Only this one has been re-zeroed. If you go Control and arrows and look at the other ones, you can tell they have not been re-zeroed.
Okay. Okay. So open the others?
Sorry?
I'm sorry. So now controls, we did 4 already, do we?
I'm sorry?
I said, we did 4 already, or earlier we did 5?
We did 4, and then it moved to 5 because that's the next one in the directory.
Okay.
But we're not going to do anything with this data. This was just for the demonstration purposes of re-zeroing manually. We're going to go back and reuse that data that we re-zeroed batch.
And that's in process.
Analyzed, yep. Yeah, go ahead and open up the top one. Okay. Let's go ahead. So what we need, remember our goal here is that we did a bunch of indents in the fuse courts, and I need a text document that gives me columns of, you know, contact depth, stiffness, and everything else so that we can feed it back into the system so that we can get that corrected contact area. The way that we do this is actually what's called a multiple curve analysis. So on the left-hand side, I never remember, I'm pretty sure it's this one. If you hover for long enough, it should pop up. So go ahead and click that. Oh, I don't know.
My mouse is gone.
Is it because of me? I've seen that happen before. There we go. Yep, multiple curve analysis. So you remember how before we clicked execute fit, and it did the fit. It did a power law fit, the first derivative, and calculated our hardness and modulus yesterday. Today, what we're going to do is a multiple curve analysis where we're going to give it all the files, and it's going to do that over and over and over again in the background. So go ahead and select all of these. Click add. Okay. And it's going to ask you for a name. I generally just call it results. We can definitely, you'll get your SOP under you as you do this.
Save.
Okay. And so you can see it's opening the file, executing the fit, and saving all that information that pops up here for each individual indent. Oh, a little noise on that one. Interesting. Okay. So what this has just done is it's opened each file, clicked execute fit, and it's gotten hardness and modulus results. Here's my question to you. Do I care about if these results are good or not right now? Or better question might be, do you expect them to be good at this point?
Kevin is not here right now, so I'm looking after this. So it looks good. Only thing is that these are the outliers point. One point is outlier, and there is a small trend that we can see is not perfectly flat.
Correct. And it's also not the expected values, right? I expect 69.6 for my modulus. Do we want to pause until Kevin's back? Sorry.
Yeah, sure.
I'm happy to pause. I just need to be notified. That's all.
Yes, definitely.
Okay. Do you just want to let me know?
Okay.
Oh, I'm sorry. Where are we? Just. Oh, you're muted, Laura.
Yep. So I want to be clear. I'm happy to take a break at any time. I just want you guys to let me know because this is like one of the most important parts of the instrument is understanding how to do this tip area function. So I just want to make sure that whoever needs to be here is here for when we're going through this process. So is now good, or should we take a longer break?
Oh no, we're good. I'm just gonna go grab a water really quick. I got it.
Oh, okay, great. So yeah, the data, it just went through and it did that where it opened up every curve, clicked execute fit, and it gave us the fit and the hardness and modulus is all saved in this file. And each one of these points are then each individual indent's hardness and reduced modulus. My first question, I have two questions here. My first question is are these results what we expect? And do I care if they are or not? So first, are they what we expect? We expect the reduced modulus and hardness to be constant as a function of depth in fused quartz, which this is not. And I expect that the modulus will be 69.9, 69.6. Thank you. Sorry, I got stuck. 69.6 plus or minus 5% and hardness 9.25 plus or minus 10%. So these numbers are not matching. It's not constant. So this data is not great. This is not the expected results. My question to you is, does this indicate anything about the system, or do I care about this data? Does this tell me anything? And if, yeah.
Of course, it matters, and both the values seems a little too high compared to the standard or the known value.
That's correct. That doesn't matter to me at this point. If you remember, what we are doing is we're opening every one of those, and when we click execute fit, we are calculating the hardness and modulus. Hardness and modulus are based on stiffness, which is from the graph, max force, which is from the graph, and contact area. Do we have a proper contact area currently installed?
Contact area. No.
How do we, why not?
I forgot the part that yesterday we did something to find out that area.
So that's what we're doing right now. We have not made a good tip area function, right? We have the default tip area function installed. That means that our current equation is the contact area is equal to 24.5 times HC squared. We don't have any of that other information. We only have the idealized Berkovich probe. So when we click execute fit, we're using that default tip area function, and then it spits out this data. And the reason I don't care is I know it's going to be bad. I know that that tip area function is not correct, but I need this, what is currently on the screen in front of us, as a tool, because this gives me hardness. Well, more importantly, it gives me reduced modulus as a function of contact depth. And in this text file is all of the other information, the fit and everything else. And so what we do is we take this and we give it back to the system and we say, okay, you know, this reduced modulus should be 69.6 for each of these contact depths. Please solve for the contact area based on that information. So my point here is that this first, when you do a, your tip area function and you're starting from scratch, the first iteration, this first results does not matter. It is a tool that we are going to use. So go ahead and click close here. And let's go to system calibration. And let's go to tip area function. And you can see here, this is where we have that default Berkovich.ara defined. Well, we don't want that. So instead, on the left-hand side is a calculate button. You might have to click the symbol. Sorry, and it's asking you, oh, what file do you want to use? And we're going to use that analyze results.txt file that you just made. That's our tool. Good. And it brings us to this calculate screen, where it has taken that data file, that text file that you just gave it, and for each of those indents, it has calculated what the contact area must be for the contact depth measured for that reduced modulus to be 69.6. That 69.6, well, not yet. We haven't clicked execute fit. It will do that in a second. But the standard sample properties, this is the default for fuse quartz. The tip properties, these are the defaults for a Berkovich diamond probe. You can obviously change these if you're using something like steel, or if you're using something like a sapphire probe, then you would need to update these to be correct, because that impacts your reduced modulus calculation. And then down here, you have your area function settings. Now, the first one is C naught if you want to do auto calculated value or manual fixed value. For most users, they're going to use that manual fixed value of 24.5 so that it describes an ideal Berkovich probe at deeper depths. Because if you note, our contact depth for this equation currently only ranges from 38.2 to 197.8. You say, Laura, but you told me I need to target the contact depths at which I'm indenting to, and that's true, but we can't really go any further in fuse quartz than a contact depth of about 200 nanometers in the fuse quartz sample. It's too hard. So what we have to keep in mind is that as the probe goes deeper and deeper, it acts more like an idealized Berkovich probe. So we want to keep that C naught set to that 24.5 to accurately describe that idealized behavior. Similarly, the number of coefficients you can go to is 6. We don't typically recommend that because it over-constrains the calculation at deeper depths. So typically we pick 3 or 4. So go ahead and change the number of coefficients to 4 for me. And then click Execute Area Fit. And so you can see now a green line, which is your tip area function, has populated inside of your data. Overall, this looks pretty good. It matches the data fairly well. It doesn't have any weird kinks from these 2 outliers that we have. I like it quite a bit, but let's go ahead and let's try 3 coefficients and see if we lose any information. Yeah, basically if we lose any important information. Then click Execute Area Fit again. Overall, look pretty similar to me. I think it diverges a little bit more at 3. So I would say let's go back to 4. Click Execute Area Fit. And go ahead and let's save this. So now we can save this, and it's up to you how you want to save it. I have recommendations. I typically save in that area function folder, and I typically save it as the tip part number, serial number, and then the date, so that way you can track your tip area function as you will have to update it, so that you know when you took it. Or you can just save it as that. So now if you go ahead and one thing I want to point out is that I've just told you that you can do indents at depths greater than 200 nanometers. How shallow can you indent using this tip area function and trust the data that you've gotten?
How deep?
Shallow. What's the shallowest you can indent and trust that your indents are correct, your hardness modulus are correct?
I'm not sure.
It's down to whatever this minimum is. So right now you're at 38.2. So my point is that you have not taken any indents in the fused quartz below 38.2, so you have not defined that well.
Okay.
Because it will diverge. So now if you go ahead and click tip area function again to get us back to the definition screen. So here you can see it's saved. This actually looks pretty good, but normally they don't converge to 0, 0. Usually there's a lot of weird stuff that happens at these lower contact depths that we can't guarantee that the behavior is correct. So this tip area function is really only valid down to about 39 nanometers contact depth. So if you wanted to go shallower in your material, you would need to have shallower indents on the fused quartz standard to define the tip area function at shallower depths. Okay, so we have now defined a tip area function. And if we were naive people, which we are not, we would say, great, the last question has been answered. I'm going to move on and do indents on my sample. Instead of doing that, we are more of a trust but verify people as scientists. So we're going to need to check that tip area function. And the question is, well, how do you check it? There's a couple answers. The one that no one likes is that you could go do another 100 indents in the fused quartz standard. But that would take a lot of time and it's not really worth the effort because we can just reanalyze the previous data using this new tip area function. Now that should set an alarm bell. You should say, Laura, you just told me that we are setting the modulus to be 69.6. So obviously the reduced modulus should be correct when I reanalyze the data. Let's say, yes, that is absolutely correct. However, we have not tied the hardness. So the hardness results will tell me the health of my system and offer any other concerns that we might need to address. Does that make sense?
Mm-hmm.
Okay. So in order to do so, we're going to do exactly what we did at the beginning with the group analysis, but with one important difference. So if you go back to the data analysis tab, there is a setting here for the tip area function. And right now it's set to saved with indent file. So whenever you do an indent, it saves whatever indent was in that screen at the time of indentation. That's no longer the same for us, right? Because that was the default. So instead we have to select to use the tip area function from the tip area tab. Okay, so now you can go ahead and do a multiple curve analysis. Or you could execute fit here too. Actually, that's a good idea. Go ahead and close this for a second. So right now, this was the old tip area function. Go ahead and click execute area fit and let's see how it updates. So now you can see it's much closer to our expected values of 6706 and 8.52. So that's true for this one singular indent, but it's important that we do all of them at once. But you can see the importance of updating what tip area function you're using by that demonstration. So you did a plot multiple curves. What we needed to do was a multiple curve analysis, but you can still do that from here. So there is this mult curve ANA, which is the same thing as the multiple curve analysis button you used before. And I like to just save over the previous result because the previous result doesn't matter. That was a tool that I used to get a relationship between contact area, between contact depth and modulus. Okay, so now two questions. One, do the results matter here? Should I expect them to be correct?
Yes.
Yes. Second question, are they? What do we think?
The reduced modulus is very close.
Which it should be, right? Because we defined that to be close. That was the tool that we used to get our correct hardness modulus.
But both reduced modulus and hardness are very close.
This,
I guess because this outliner thing, which we saw earlier.
one indent out of 200 probably isn't going to make that much of a difference in this. We probably should have removed it, but it's nice to see it so that you know what you're looking at. What's actually probably impacting it more is this drop off. So in order to have hardness, you need plastic deformation. Berkovich probes start to get blunt in between like 30 to 60 nanometers, depending on the radius of curvature. So that's what that drop off is. So if we actually take it and put it in the section I would expect, you're at 9.2, which is, so that takes it between here and here. That's where this is calculating between, which is exactly what I would expect. So I'm looking to make sure that your 69.6 is very, very close. 69, it should be very close on the modulus. And then I'm looking for the hardness to make sure in this regime that it's 9.25 plus or minus 10%, which you are easily beating. Does that make sense? Are we on board with that part?
Yes.
Okay. The last thing I'm looking for is any sort of trend to the data, specifically the hardness. If you're seeing a slope in either direction, so if it's sloping upwards in hardness or downwards in hardness, that should throw a red flag. We know that the hardness of fused quartz is constant as a standard of depth. If it's not, if you do all this data analysis and you're getting a trend, that usually indicates a problem with machine compliance. If you remember, there is that setting. Can I click it when it's open? Probably not. No, there's that setting in the system calibrations tab. We'll go look at that here in a second. The machine compliance calculates the compliance of the entire system. So, let's see, the table to the floor, the table to the steel plate, well, the table to the feet, the feet to the next feet, so on and so forth, up to the feet to the granite to the XY stage, to the sample stage, to the sample, to the mounting, and on the Z, right, goes up and over, the Z granite to the XY granite to the Z stage to the dovetails to the scanner to the transducer to the all of that compliance, meaning whatever compliance is in that system is what we're looking for. And if we see a change in hardness on the fuse cord standard, we typically see we're typically looking at something's wrong with the compliance. Either one, the compliance is set incorrectly, or two, something has gone compliant in the system. I specifically do not train users on how to resolve that issue, because if you see a problem with your compliance, I want you to call me. I want us to have a conversation about it, because 99% of the time, and I really wish that was an exaggeration, the compliance, sorry, let me back up. Jim set the compliance when he was on site, and he said it well based on this data, how there is no trend here. It's very nice and flat. If all of a sudden you're seeing a trend in your compliance, if you are seeing a change in your compliance, it almost always is the sample or the sample mounting, meaning it's not being held to the magnet well enough, or a couple years have gone by and the epoxy that holds the sample to the AFM puck has gone brittle or something like that. And I want us to correct the root cause, not calibrate to an incorrect compliance. So that's our training on machine compliance, is know to look for a trend in the fuse cord's hardness with a proper tip area function. And then call me.
Okay.
Okay, does that make sense?
Yes.
Okay. So I have homework for you. We're not done yet. I mean, it's only been an hour. After we get off the phone today or tomorrow, whenever you have time before our next meeting, I want you to take that raw data and I want you to do this again, and see if you can create the same tip area function and get the same results as we got during this session. And if you're struggling, then we'll know where we need to target to make sure that we understand what's going on.
Yes.
Okay. That concludes tip area function and machine compliance. It's a really big topic, and it's probably the most important one to understand. But at the end of all of this, if you have done all of your things correctly, and if nothing is broken and you are getting good results, at this point, you can be confident that you are going to get good results on your sample as well. So you can then begin to test your sample. So you can see why it might take anywhere between 2 to 4 hours. If you've got a good tip area function, right, then you don't need to do the indents on the fuse cord standard. There are a couple of comments about the tip area function I would like to make. The first is, the question I asked, that last question is, do you have a good tip area function? It's not a demand, right? It's not perform the tip area function. And if your answer is, I'm not sure, what you can do is you can do 3 or 4 indents in the fuse cord standard and see what your results are. If they are good at the contact threshold that you intend to test to in your sample, then you can be confident that the tip area function is correct. If they're not, then you're going to have to run the 100 indents.
Okay.
If you are targeting those lower depths, you will need to go to lower forces on the fuse cord standard to make sure that you're getting this. Any data basically underneath 38 in your sample, I wouldn't be able to trust because we didn't define it well there. And I have no way of knowing what that tip area function is doing at that point.
Okay.
Oh, the other question I always get is, how often do you have to do it? How often do you have to perform this tip area function? And the answer is the worst answer any technician has to ever give, which is, it depends. To go back to those two extremes, that I have a customer who's testing soft thin films, and he runs, maybe 10 samples a day. And I think he updates his tip area function once every 6 months as a matter of protocol. And it never changes that much. His tip doesn't wear down. It's diamond on soft samples. It's pretty standard. Then on the other end of the spectrum, I have what I affectionately call my concrete guys in Iowa who are testing on concrete, which is really rough on a probe, and they have to do a tip area function every single time they sit down with the instrument because the wear from the previous testing has changed that shape enough that it's important. So generally, you know, in a mixed use facility, I'd say start checking it at least once every couple weeks, maybe once a month. And you'll figure out kind of what your protocols are as you guys begin to use the instrument. But it is something that you should be aware of, is that it's really hard for me as a service engineer to give you an exact SOP of yes, every 3 months it has to be done. Really depends on what you're doing with the probes.
Yeah. I guess if we like use it a lot, probably like every like once a month, but if we haven't been heavily used like every couple of months.
Yeah, depends on the materials too. If you're doing soft, squishy stuff, what's probably more important is cleaning it, to be honest. Because if you do soft, squishy stuff, it can like get coated on the side of the probe.
Yes.
So that's stuff to consider. So yeah, I think people forget, you know, these instruments are highly scientific and it feels kind of unreal sometimes. And I think people forget that it is a very physical act that we are doing. Nano indentation is a very physical thing, right? So what's happening physically is just as important as what you're seeing on, you know, anyone can do an indent. Whether or not the indent is good is a totally different question. So these are the questions we have to consider. I have a colleague who likes to say nano indentation is not easy, and it is a trivial statement and also true, which is very annoying.
Okay.
Okay, so that kind of concludes our conversation on tip area function and machine compliance. At this point, you should have been able to load a sample, you would define it, you would do your quick approach, and then you could start doing indents and trust that you were getting proper hardness and modulus, assuming that you have set up everything else well. You know, good sample mounting, you're indenting in, you know, above 38 nanometers, all that stuff. Any other questions at this time? I expect that there will be more questions later, but it'll have to percolate.
So the tip area function calibration is only on the fuse cord. Okay. Or another sense, like let's say I calibrate today and everything looks good. I've been using it for a couple of weeks, and my data, after the my brain freeze.
Take your time.
After the tip area function, so when we do our sample, we shouldn't really need to apply for. I mean, this should be automatically applied for all the other measurement I do. However, but when I do my measurement, let's say if I see the data is a little funny, is like jumpy or fluctuating, that I guess that's one of my cue that either the tip need to get cleaned or I need to do another one. Okay.
Correct. Yep, you are absolutely correct. If it's jumpy, yeah, I would expect a dirty probe. If it's just all of a sudden, man, I tested this sample last month and it was, I don't know, let's say 9.25 GPA, and now all of a sudden it's 8.25 GPA. Like that seems like a big enough difference that maybe the problem is the tip area function. Or it's that your tip area function is not well defined at those samples, or we can see a lot of drift. Yeah, basic troubleshooting is kind of always, even if you don't redo the tip area function, if you're getting weird results on your sample, the first thing I do is run that same test on the fuse quartz and see what happens. We have an expected value for that. If we're not reaching that expected value, then the search is on to figure out why. Versus if we can do it on the fuse quartz and we can't do it on your sample, then the questions I would ask would be, what's different about this sample versus the, you know, the fuse quartz? Because at this point, we would be confident that the system is operating well. So then, okay, I would look at sample mounting. Did I use double-sided tape even though Laura said not to? Did I use whiteout? Is the magnet not held down well? And then thinking about the sample itself, is the surface rough? Is it dirty? Could it have become contaminated? Can I clean this sample? Clean the probe? And then, of course, you know, how rough is it? I might have said that already. My apologies. And then am I indenting in a well-defined region of my tip area function? You know, meaning okay, you went to 500 micronewtons in fused quartz and you went 39 nanometers contact depth. And you think, great, I did 500 micronewtons. So you go to your sample and let's say it's a diamond-like material and you go to 500 micronewtons, but you're only traveling 10 to 15 nanometers. There is no reason for us to expect that the tip area function is well-defined at 10 to 15 nanometers, even though it's the same force, right? Because that's a displacement relationship. So then we would need to think, did I define it well in that place? And if not, we'd have to go and make sure it was well defined.
Okay, so another question just jumped to my mind. Might sound dummy, but
No.
so earlier when we can I close this?
Mm-hmm.
Yeah. So earlier, when we one before that, after we analysis all the graph, like if I click Excel feed, it's still just have the one data, and I cannot add them all of them here.
Correct.
Okay. Okay. Good.
Yep.
So earlier when we do the automated test and we define, is it here or in the, yeah, here in the perform test we set up that the tip will touch it and then it will increase the force until, let's say, like 2 seconds and then unload.
Mm-hmm.
And then after that, we'll go with the serpent pattern, like go like in this way. In that sense, the indentation I will assume should be the same depth.
We're changing the force. So you would be correct, except for that we changed the load function. So in this screen, can you click that load function tab here? So here we're changing the peak force.
Oh,
so we're
yeah,
starting.
Yeah. You're right. You're right.
It's okay. This is a
Yes,
lot
I
of
got it.
information in a week, even in a day. The trainings things don't quite settle, right? So no problem at all to repeat.
Yeah. Now I clicked. Thank you.
Good. Good. That's what I like to hear.
Yeah. Okay. Oh, another thing is like the value, so we can also like reverse it, right? Start at like 500 and ends at like 10,000 or something.
So you technically can. I typically don't.
Okay.
There are two reasons. The first is debris. I've never actually seen this happen, but that's because I never run it that way. So that if you think about your probe, and you've got a little piece of debris right on the end of it, if you start low and go high, you run the risk of just like hitting that debris every single time. Versus the hope is that if there is any debris and you hit it, you push it up and out of the way on the first big indent, and then it gets smaller and smaller. Or
Yeah,
sorry,
right.
then it doesn't matter. So that's reason one. The second reason, which I think is a more compelling reason, it has to do with drift. So if you think about that automation, there's only really one big move, right? Going from optical view to tip and contact. That's a really large move if you're looking at your instrument. And then each indent after that, right, is only a 5 micron move. So it, moves this big move and then it comes over and it basically does this. It's not moving a lot. That means that the biggest drift that we're going to see is on that first indent. Well, it's going to have the lowest percentage of error at the biggest displacement.
Mm-hmm.
Right?
That's
1
right.
nanometer per second on a 200 nanometer indent is not nearly as bad as 1 nanometer per second drift on a, 50 nanometer indent? Or 40 nanometer indent. So that's why I like it. But well, and then third reason would be your tip area function should head towards the default as you go to deeper depths. So those data points technically matter the least. So it can be driftier. And if it is driftier and I have to get rid of that data point, if it's an obvious outlier, I'm okay with that. That doesn't really ruin anything.
Okay. Thank you.
Good. Okay, so that concludes tip area function and machine compliance and kind of all the nuances around that. Like I said, I want to have you, before our next meeting, I'd like you to run it again on the raw data, just to make sure that it kind of can stick. I think struggling through it on your own is a good first step. And in this case, we have a known outcome, meaning that we know what the result should be.
Mhm.
Our remaining outstanding topics are now imaging, property mapping, and Scratch. I believe for the three, I'm just going to pull up my email just to make sure that we're all on the same page.
Yeah. So for the Scratch, there's one. Are we going to talk about where too?
We can talk about where it's a difficult thing to talk. Well, it's not difficult to talk about. It's that none of my customers use it. In the 6 years I've been with Bruker Heisotron, I have had 2 customers who have done wear testing seriously. And it's one of those things that if you decide to do wear testing, I'm always happy to hop on a call and have an hour-long discussion with you on wear testing. That is not a problem. There's no expiration date on that offer. I generally don't train on wear testing because it conflates everything else in a user's head between indentation and scratch. And so we certainly can. I just don't think it's useful at this point. I'd rather get you good with the other parts of the instrument. And then if you find that you need wear testing, I want you to call me and I'll hop on a phone call with you and we'll talk about it in depth together.
All right. Sounds good.
Good. It's basically just imaging at higher force. So instead of just tracing it, you like wear away. And you calculate how much material you've worn away. And I can tell you some interesting things. The other secondary reason I don't do it when I'm on site is I really hate the idea of adding additional wear to a customer's probe. So that Berkovich probe right now is nice and sharp. And if we do a bunch of wear tests, we're going to blunt it down. So that's my other kind of more practical reason for not performing wear testing training.
Okay.
Okay, so I think I'd like to launch into imaging and property mapping. Before we do so, I would like to take a quick, let's say, 5 to 10 minute break.
Sure.
And then we can get back to it. So, okay, I will be back shortly.
Thank you.
Thanks. I know, I'm back whenever you are, but no rush.
Yes, Laura, sorry, give me a few more minutes, please, sorry.
Of course, no problem. Take your time.
All right, I'm back. Now you're muted.
Okay, I think I got it working now. Just, can you hear me?
Yes.
Perfect. Pretty well, or is it jumbled?
So far it's good.
Okay. Okay, so let's go ahead and let's start talking about imaging. So let's click the SPM. Well, let's go to sample navigation first. Actually, what do we need to do before we do anything else today?
I guess just imaging.
We have to do an indentation axis calibration because it's a new day. We should do it at least once a day-ish. So let's go ahead and let's go to system calibration. Good. Hey, this looks good to me. It actuated. We can see again some of that low frequency noise, but it's within what we would expect for this system. It actuated well out to about 4 microns. We're fitting from 0.8 to 3.5. The blue fit is nice and linear. There's no discontinuities in the red line of travel. And our RMSE is less than 5 times 10 to the negative 5. So this looks pretty great to me. So we can go ahead and close this. Now we can go to the sample navigation tab. And right now we are focused above where we had previously taken indents. So after the automation was complete, it would have gone back to that optical location. So let's go ahead and just move a little bit so that we are in a fresh area of the sample for imaging. Keep in mind, it doesn't have to be a lot. Yeah, that's probably sufficient. Sorry.
This is still under recording, correct?
Yep, I haven't turned it off.
Okay.
Yes, it is still recording.
Good.
Thank you for checking.
Good. Okay, I moved.
Okay, now let's go ahead and let's go to the SPM imaging tab.
Okay.
On the right-hand side.
I'm sorry, can you repeat?
Go to the SPM imaging tab. Great. So this doesn't have a lot in it right now, but we'll go through almost all the buttons, I think all the buttons and everything else that's here. What's important is that we need to do the approach. So if you remember, our system is an optics-led system. So wherever we're focused, our tip is going to come into contact there. So we're now over a fresh part of the sample. And on the right-hand side are, again, a bunch of global imaging settings. And there is a button there that says approach. And it's trying to show you, I think, the sample going under the probe, although it's not very clear. Go ahead and click that approach button under the, good. So this works very similar to like a quick approach or the approach for an indent where it's going to pick the tip up to the Z fly height, and then it's going to move an X and Y and then bring the tip down and into contact with the sample surface. Coming down and Z. Extended, searching for the sample surface. Okay, and now we're in contact with the sample. We can tell in one very big way. Up in the upper left-hand corner, do you see where the sample force is?
Up left corner here.
Mm-hmm. Further, like the far upper left. Up at the top here, there's this ribbon, right, where we get the sample force that we were looking at earlier, because we were discussing how it should be 0 when it's in air, right? Well, now it's hovering around 2 because we're in contact with the sample surface at 2 micronewtons. From here, all of a sudden, we get a bunch of new buttons that have appeared to us. So the button that used to be approach is now withdraw. So approach and withdraw go between the optical view and the tip in contact. And then you have this disengage button. So if I click disengage, maybe it lets me. Oh, there it goes. It's going to go ahead and disengage the tip it moves it up 100 microns above the sample surface. But if you physically look at the instrument, you can see it's still present above the sample surface. So this is really useful because you can be in imaging mode for a long time. You know, once you approach the sample, you can kind of try and stay with the tip above the sample surface for as long as possible. It's useful for reducing drift and a couple other things. But I'll have you go ahead and click the engage button again to bring the tip back down into contact. Good, and now you can see it's approaching again. Okay, so now we're back in contact. So on the right-hand side of the screen, we can look at the SPM imaging global settings. We have our scan rate, so how fast are we scanning each line. We have the scan size, so how many microns, how big is the scan. We have our set point, which is 2 micronewtons by default. And we have our scan resolution, which is how many lines do we take for the image. So go ahead and let's click start and let this begin to image and see what we see. Well, that begins, I would like to talk about how imaging is performed. Because if you recall, one of the things that I wanted to talk about was like where you get data from which pieces of the instrument, because in those load displacement curves, all of that data is taken from the transducer itself. Imaging is an interplay between the piezo scanner, so that tube, and the and the transducer itself. So how it works is the transducer is the transducer is sensing the force, and it's supposed to stay at 2 micronewtons. It's in feedback with the piezo scanner, which is currently moving in X and Y back and forth. And as it moves back and forth in X and Y, it also moves in Z to keep that transducer in contact at 2 micronewtons as close as it can. So what we're seeing here is all information from the piezo. However, we're not seeing a lot. So right now our image is still white. And we're seeing this down here, we have topography versus lateral displacement, and we have 2 lines, which we'll talk about. We can see very obviously that there is a sample tilt here that we need to address. So the first thing I want us to do is go to what's called the BG, which is background subtraction. So go ahead and hit that. And you have 2 options here. You get linear regression and zone. If you save the image in the post-processing, you can always also do average plane. But that's not an option here at this time because you don't have a full plane.
Okay.
So go ahead and hit linear regression when you are ready. You can go ahead and click close.
Okay, I'm sorry, I'm driving.
No, it's okay. Take your time. Yep. And then go ahead and click auto here. Sorry, below the histogram. Sorry, that was unclear. Those were unclear instructions. There's this histogram here that defines the coloring on this graph. So go ahead and click auto and it will give us better contrast probably. About the same. Looks like it did it maybe when we applied the background subtraction. And then down here in the scan line profile, you can see we're no longer seeing that big slope that we were seeing before from the sample tilt. So it's been effectively taken out. So yeah, this is the basics of imaging. How fast do you want to go? How big do you want your scan size to be? And what scan resolution do you want? Here's how you take out the background subtraction. Yeah, here's what we're looking at.
So one quick question, like the blue and then the red line, earlier when we were using our AFM, I was told like the blue and then the red line, one is like left, one is right. So basically you just see whether you're matching to each other. And this one matches okay, not too bad, but obviously it could improve.
It can't You are correct that they do not match exactly. It can't improve. That's the hysteresis of the piezo. The longer we wait, it might get slightly better, but it is expected because this is an open loop piezo. Keep in mind, we're not an AFM. But you can actually see the difference. So here we're looking, you get 6 images out of this, topographical, forward, or reverse. So you can actually see the hysteresis and how the image shifts.
Mm-hmm.
It's expected behavior of the piezo is how I would put it.
So after you finish, you're gonna come back?
I'm not sure. What do you mean come?
You see now is like going down.
It will continue to just go up and down in image indefinitely. It's not done. We didn't ask it to do anything. We didn't ask it to save anything. We just said image. So it's just going to scan that sample surface until we stop it, or until we stop it actually, even if we save the image.
Okay. So like the scan rate, I know one is a standard. I don't know, like with AFM, the scan rate, if we scan like slower, the two line match is better. I don't know whether it is the same thing.
Probably true. It probably helps with the hysteresis, but it doesn't really impact anything here. I'm not sure what the goal is for the AFM. The goal is to get the piezo, but for us, the goal is to get a good image that you can make good indents in, either by observing or everything else. Like no part of my training encourages trying to get those to overlap as well as possible.
Okay.
It's not important for our system. We are not a closed loop system. We are an open loop piezo scanner, so it's going to have higher hysteresis than an AFM. It's not a one-to-one comparison.
And then there's offset. Do we need anything?
Yep, so we're going to go through each of these one by one. I just kind of wanted to be like, here are the basics. Here's what an image looks like. So you have some options here. Primarily the point of choosing to do an image with a nano indenter is to find a good point to perform an indent. So I'm going to go ahead and turn the reticule on. And so you can perform individual indents from imaging. And I'm looking at this and we're pretty close to some of this other junk. So I would say let's go ahead and we're going to move slightly and then we're going to perform an indent at that location. We have 2 ways of being able to move to target a location. There are these piezo offsets, which will offset the piezo scanner in X and Y to try and target where you're telling it to go. You're welcome to use those. I generally don't unless we're trying to get really specific on where we're hitting, meaning like within nanometers, hundreds of nanometers even. Generally speaking, the stages are just fine for most uses. The only reason I discourage the piezo offset slightly is just that putting a large voltage on a piezo material ages it. So the longer you sit there with it having an offset applied to it, the more chances you run of aging that material prematurely. So generally I like the stage movement a little bit better, but there's nothing wrong with using the piezo offset should you need to. Now that being said, I want to move away from those, and this seems like a pretty good place to me. So let's move in X -3 microns.
While it's imaging?
Yes, you can do it while it's imaging. I wouldn't do very, very, very large stage moves, meaning like 50 to hundreds of microns, just because of sample tilt. You have this Z piezo here. It shows you how far it's extended. We're nominally in the middle of the range. You get 4 microns total, so plus or minus 2 microns up and down. So if you have a really tilted sample and you make a really big stage move, you can run out of range either at the top or at the bottom.
It's like X -3 move.
Yep. And then to make this more interesting, let's also, once it's done, let's make our scan size smaller. Let's go 5 micron, 6. Sorry, I'm deciding. Let's go 5 microns. Okay, and you can see it update it updated live. It did start from the bottom here. So we could wait. I'm going to say let's go ahead and perform our indent, then we'll image our indent and look at that image as well. So let's go up. While this is imaging, we can get our sample, or excuse me, our load function ready. So go up to the perform test tab.
Perform test?
Perform test tab. Yep. Nope, the tab. Sorry.
Oh. What is that for?
I'm about to show you. So let's go ahead and let's load the standard QS trapezoid load function from before. So if you go over to the hamburger button menu, if you remember, this is the same load function screen we were in earlier. Yep. Okay. Let's change this to 10,000 micronewtons peak force. Okay.
Oh.
Is that where we wanted to change that probably?
No.
There's another setting that we can input to change the whole graph. Do you remember where that setting is?
Here.
Yeah, great. Okay. Now, I want to perform this test while we're like at the center of the image. That's the only option you have. And so you have here perform indent, start, or in SPM imaging, you also have perform test. All three of them will do the same thing. They all perform whatever test is currently loaded in the load function. So if you have a scratch loaded, if you have, you know, just a regular indentation, like it will just do whatever is loaded. So it's up to you to make sure that you have that correct before you come in here and click perform test. But let's go ahead and do so. And you can go ahead and click start. And this should look pretty familiar at this point after the indents that we've done. There is no motor settle time because we're not moving the motors. We're only moving around the piezo. So we still do have our 45 seconds of piezo settle time.
So the piezo is the ring thing that clamped the tip, right?
No. Let me grab the manual.
But I see it small.
Trying to find an image of it, sorry. Okay, so I'm gonna go ahead and share for a moment here. Okay, so this is the transducer. This black U-shaped part. Are we on board with that?
Yes.
And then your probe goes inside the transducer. So transducer, probe. So here's your transducer and probe together. Then your transducer mounts to the piezo scanner, which looks like it's the best way of demonstrating this. Sorry, I'm trying to find a good picture just to demonstrate this. Um, so the piezo, this part, so this part is the transducer as it slides on this housing into this tube. That's the piezo.
Okay.
Yeah, so the tip goes to the transducer mounts to the piezo scanner.
Okay.
Does that make a little bit more sense?
Yes.
So inside of this tube, I have a really good exploded view. I'm just trying to find it. Sorry, this just will take me a second. Come on, where is my mouse? This. This is what the inside, so this tube part has a little dovetail at the end that the transducer sits on. This is what the inside of that piezo scanner looks like. So that's where it's sitting, is on this XY. Is today a good day for training? Because we could also take a break and pick this back up on Friday if that would work better for you for retention.
It's fine.
Okay, if you're sure. So yeah, here are those quadrants I'm telling you about. So we're applying voltage right now to this X and Y to cause that tube to shrink and contract to make it do this.
Mm-hmm.
And then the piezo, or the transducer sits at the bottom here like this. And then the probe sticks out so that that travels over the sample surface as this adds and subtracts voltages.
Okay.
Then I'll have you start sharing your screen again whenever you're ready. I'm just gonna close these blinds really quick because they make me look very. It's a little bit better. Okay, so go ahead and save this data, maybe in the fuse quart. What did we do? A 10 millinewton fuse quartz?
It's all the same.
I'm sorry?
Is out of the same file? Is our HYS file?
HYS files are the indent files that the indent files. So this is the indent that we just took, right? We just took an indent like we did from from optics before.
Yeah.
So this is like a 10 millinewton fuse quartz image indent. Yeah, that works. Yeah. Okay, so we have an indent and it's done, and now it automatically starts imaging again. So the thing about imaging is that you really shouldn't walk away because it's going to continue to image until you stop it. So it kind of needs to be a user performed test. So we save the indent. Now I want to save the image. So I want you to go up to the hamburger menu. And let's go to image, capture file name. And let's go ahead and let's go to browse folders here. And I'd get back to that folder where you've been saving our data on the desktop. I think it's under Kevin. And then you can go ahead. I'd make a subfolder here for images because each image file saves six files, which can just clutter a lot. So I'd make a new folder.
Yeah.
I call it images. And and then click into that new folder. And then go ahead and click done. All right, and go ahead and click close here. So now we told it, oh, well, we should probably, sorry, can you go back there to the hamburger button image? Yep, capture file name. And then let's go to, I like to call it the same base file name as whatever the indent was. So in this case, it was 10 millinewton image indent. Oh, no, sorry, not the folder, not the, my apologies. You can leave that as images. Click back into there. And then click done. No, click done here. And here, sorry, there's this image base file name. Right now it's just called in situ image. So let's go ahead and rename that. Yep, sorry, my apologies.
See that indentation?
Yep, so go ahead and click close here.
What is that line? Right line.
And then
Good.
go back to the hamburger menu. And click image. And then click capture. Yep. So what you'll see here is that a little camera popped up. So it's going to finish taking the image and then save that as a .bcrf file, which is also a very common AFM file name.
So Laura, what is this wide?
Yeah. So that is a product of the line by line linear regression averaging. So go ahead and click auto again on the histogram. Good. All right, so you can still see it here. So when you do linear regression for your background subtraction, that's a line by line. So that means that we're thrown off here because the deepest part makes this look lighter. It's not real. It's an image artifact based on the background subtraction of the linear regression background subtraction.
Okay.
Does that make sense? As we're traveling over this, right? When it does a line here, all of the is relatively the same versus when it traces here, this is suddenly much deeper than the sample surface. And so that difference, when you do that average, makes this look much lighter than it does to the north or south, because we're averaging between this and this.
Oh, your mouse is not moving.
Oh, no, sorry.
Oh.
Yeah, my camera also ditched out there for a second, but I think I'm back. Okay. Yeah, so when you draw, so it's scanning line by line here.
Mm-hmm.
And when it scans here, this surface is all at relatively a similar height. Yeah, there's, a couple nanometers maybe, not even, a couple nanometers maybe of tilt that we have corrected for with the background subtraction. So that means when it takes the average, they're all at relatively the same length, or same height, excuse me. Versus on this line, or the lines around it, if we draw a straight line here across, on that pass, these are two now very different heights. So that makes this look artificially high, because the average is somewhere in between the two of them.
Is it like the hysteresis?
Nope, it's an imaging artifact. It has to do with the line by line. So if you think about, let's see. Okay. Here we go. You have a sample, right? And on the sample, it's tilted, but you're scanning this way. That means that if you think about where the average color should be, it wouldn't be here at the top and it wouldn't be at the bottom. It'd be around here, right? And this is not so different than this average, then is so different than here. However, if now you add a giant indent into it, for the sake of the comment, this is not the best, but just, bear with me here. Now, all of a sudden, that's kind of triangular. Your average plane goes from, here to here to also including here. That means that that average no longer is between these 2 points, but it's down here. So the average color is somewhere between this bottom point and the sample surface color, which means that when it traces here, this average, this is now artificially conflated as higher than the average. So it's really just an impact of the background subtraction and how it operates. And I can prove that because if we go to, well, first things first, I don't want to leave this scanning forever. Let's go ahead and disengage the tip from the sample surface because you can see we are now retreating. We're going back down and our image is done. That means it's taken the image for us. So go ahead and disengage for a moment while we go. And I need you to open up the TriboView software, which is in your, in Windows. Yeah, or perfect. Okay, now there's an image folder path, so go ahead and select. Or choose image folder, that also works too. And then go to where we save those indents under Kevin. Good. Under images. And there they are. So you get 6 images for each image that you save. So go ahead and click done here. And they will populate. So the first 3, if we hover over the, well, you might have to do it. Will it let me? Okay, so do you see how this says GF at the end? You have your base file name and then GF. And then this is GR, GV. This one's TF, TR, and TV. So you get 3 gradient images and 3 topographical images. The topographical image was what we were looking at in the TriboScan software. We just happen to have that one selected. You can look at the other ones. The topographical is the Z piezo data as it goes up and down as it scans the sample surface and tries to keep that transducer in contact at 2 micronewtons. The gradient image is often called the error image. That is from the transducer, and that is the variance in force around that 2 micronewton set point. For the purposes of the question that you just asked, let's go ahead and open up first this TF, this topographical forward image.
This one?
Yep. And it's going to pop up in a new window. I'm going to do a little trick here. When we're working in TriboView, I find it's best to make this smaller so that you can still access all of this and also still see the image. Okay, so here we have many of the same commands we had in TriboScan. I want you to go to the background subtraction. Tab, I should make that more obvious up here. And you can see now we have linear regression and we have zone, but now we have average plane because we have a full plane with which to average that over. So if you go ahead and click average plane, that imaging artifact goes away. Because instead of averaging that singular travel point where it went down to the deepest part and then back up, right? If we think about that, then it put for that singular line. Now it knows that the average plane, if it takes all of it, is all roughly the same color. So it knows not only the average this way, but also the average this way, and is able to correct for that accurately. Okay. Some other cool parts about TriboView. So what I'll say about TriboView. TriboView is a great program. It does what it needs to do. You can do a lot of stuff in it. That being said, have you ever used Gwydion?
Yes.
You can also open these files in Gwydion.
Perfect. I was going to ask you because I use Gwydion a lot.
Yeah, so I'll just show you a couple things here then, because I would recommend, TriboView is great. It does what it needs to do, but Gwydion, if you're familiar with it and if you're comfortable with it, you're probably going to be able to do a lot cooler things than TriboView can. TriboView, I can draw a line, twirl it around, see some information that way. I can, let's see, so we have browser, so you select the one, you have selection, so where we're looking, gives you some information. Here you can look at things like, you can put a cursor here and a cursor there. Oops. Keep in mind, it's really difficult to image an indent with the same probe that made that indent. It's physically difficult, so that can be hard, but this does show you, where those lines are. This can be useful if you're doing things like fracture toughness testing, because then you could measure the fracture crack. Get the histogram, which is the same as it is in TriboScan. We can update it for this. We talked a little bit about background subtraction, color tables, so you can make it different colors. Super fun. What I like is the 3D plot. Sorry, there's a little lag here. So you can get this 3D plot of your image that I think just looks really nice. You can actually, move it around, see underneath it, those kinds of things. So yeah.
Can it understand?
Yes.
What form?
The T, I forgot. Is it T? So Laura, one question. So I know all the image can be read by Gradient. So the AFM, our AFM image, I think is T file, so it should be also accessible to this, I assume.
Are you asking if the AFM files will open in TriboView?
Yes.
I don't know. I can't guarantee that. I can only guarantee that images taken by my instrument will open in TriboView.
Yeah, we'll use Gradient.
Yeah.
And one more question, Laura. For this imaging, is there a how should I say, sensitivity or the roughness range that this tip can handle?
Well, it's more that piezo scanner, right? So we were talking about that Z. So can you bring TriboScan back over to this screen for me? Please.
Is this where looking?
Sorry, TriboScan. I wanted to see the TriboScan software. Too many Tribos. So you have this piezo. I recommend keeping an eye on it. The concern with a rough sample is that you run out of range, and running out of range, bottoming out, not so bad. You're not going to get an image, right? If it's trying to reach the sample surface and doesn't have enough range in the piezo to do so. But if it's fully retracted and in contact, there's nothing the system can do to get that tip out of contact on its own. So if you're imaging and you have a really tilted sample or a really rough sample, you do run the risk of causing damage to the tip if you're not paying attention. So that's one thing. The other thing I think about when it comes to roughness is that we are using a Berkovich probe, which is a very, very different beast than an AFM cantilever, right? I'm pretty sure if you graph them next to each other, the cantilever would look like a knife and the Berkovich probe would look like a volleyball. It's just so wide. And so if you think about trying to image, like, let's say it's a step, right? And the step is narrow or it's rough and it's narrowly rough. There's no way that the probe's going to actually make it all the way down, right? It's going to come through and kind of, and then move back on. So those are things to think about when you're thinking about how rough. The common rule of thumb is, yes, you can indent up to 10. If you want to indent a rough sample, you can. You have to indent at a contact depth that is 10 times deeper than that sample roughness. So you technically can, but then my question always is, why are you indenting a rough sample? Is this really the best use of a nano indenter? What information are you trying to get from this rough sample? And then the other question is like length scale of roughness. So is it locally rough? And there's a smoother part out here you can test. Is it generally rough, but has, like the Rocky Mountains are rough, where there's valleys in between them that are nice and big and wide, that you can indent into there. So it really depends on your sample and what you're looking at.
To drizzle which type of hole, right? You can indent that and then deposit this. And we indent on graphite.
Oh, yeah. So our postdoc just asked a question. Earlier, we were trying to coat on a battery electrode, which is a cover based on graphite powder or a paste on the top surface. So earlier, where that graphite on the top is fairly rough, is around 5 to 10 micron, and we're targeting only coated, let's say around top 20 nanometer, which is very small compared to the roughness of it. So earlier we were thinking to coat it and we're coating our oxide material on the top, and then use our SEM to coat like a small area of the platinum on the top, and use FIB to like cut a cross section, and then tilt it and view the section by section. So our Dr. Nico just asked a question. For example, if we have our substrate as our electrode and we indent, that will, let's say, get like a 5 nanometer or 10 nanometer hole, okay? And then we're gonna coat it. Let's say we indent it for like 10 nanometer. When we coat, I measure the roughness or imaging it, and then we're gonna coat, and then we're gonna match the imaging again with the same area, and hopefully that can give us the difference, which will be the thickness that we coat. Is that feasible? If we can find the error, if we can find a spot, first of all.
Right. I mean, I'm still at the first part of indenting into something that's 5 to 10 microns rough. Your transducer only goes 5 microns. It's in the roughness of the sample. There's no guarantee about what it's measuring at that point. You wouldn't get accurate, excuse me, hardness or modulus results. In order to, if it was the opposite, if it was, 5 nanometers, but my question is when it's 5 microns rough, okay, you want to do a 5 nanometer indent into what? What are we looking at there? What are you indenting into? Because if you think about it, it's like all these little tendrils, and you're gonna hit part of it, I guess. And you're not going to be in contact well enough to get good hardness and modulus. You wouldn't have an accurate area, right, to be in contact with.
Let me jump in. We are, let's say, we are using the battery electrode. Battery electrode is like graphite powder. So we are not interested in finding the properties of the graphite powder. So we are not going to find the hardness or the Young's modulus. We are interested in just a indented mark, so that we can use that the groove and deposit something and see in the SEM the thickness that we are going to deposit using ALD or something like that.
So the thing is, Laura, because it's like rough, we are trying to, like, the surface itself is rough compared to the oxide material that we want to coat on the top. So we want to compare before and after to see how much we coat. I mean, theoretically, we know how much we coated on it, but it's experience-wisely, since it was so thin on the rough base, it's hard to characterize, and especially oxide material is, I mean, it's clear, like, you know what I'm saying? Like, it's so thin that we cannot see it.
You certainly couldn't image something that rough. So getting, not without damaging the probe, certainly. And I really don't know what the transducer or piezo scanner would do with a sample that rough, besides give you really, like, I don't think you'd get a good image with the system in the first place, which kind of calls into question the first step, right? Because you want to image and then indent somewhere and then go fill it and then come back and image again. I'm just not sure how that's going to happen in a way that would let you at all target anything meaningfully. And It sounds like your structure, it's an electrode. The problem is that you want to get back to it, and getting back to it's going to be the difficult part.
Can we indent on a powdery surface like a graphite?
Well, we were talking about its roughness. What do you mean by powdery?
It's powder, basically graphite powder.
Is it
A few particles. I just want to indent and make a hole on a powder. That's it.
how big are the particles?
How big is a particle?
Like 5 to 10 nanometer, micron.
5 to 10 micron.
On a smooth composite material from imaging, you could do that. There's no way you're going to optically be able to do it, and it sounds like it's going to be too rough for you to image on it to
No, image we can do the SEM, right?
yeah.
I'm just
My point is that if you want the indent to land precisely on, you know, on a particle, right? So let's talk about it like it's a composite material. My concern about graphite, a powder, I'm wondering how that's mounted to the sample. Like that concerns me. If it's just sitting on there, what that means for doing nano indentation on it, I'm not sure that that's what that looks like.
Is a composite. Well, it's powder but glued in some material, so it's
Okay.
is like a sheet.
Okay, so it's more like a composite material than it is like a powder on a sample. Where are you?
Yeah, no, I don't know whether you're able to see.
Don't do.
I mean, it looked like a paper literally, and on the
Okay.
paper there's some like a carbon powder on the top of it, and you see all the black are carbons.
I'm sure you're not the first ones. And the problems that I'm seeing, you know, the answer is always, we're certainly going to try. But I do have, you know, so you want to land on a 5 to 10 micron composite material. Normally with customers do it, oh, is there a problem? No. When customers use a composite, they're it's stiff enough that they can polish it down to one. Sorry, do we need?
No, they're making some noise. I just told them
Okay.
to pause.
You know, normally when we're looking at a composite material, people are polishing it down, and then scanning it becomes easier, and then you can start to target those composite places. Like here, right? I mean, this is fused quartz, so it's very boring, but you could imagine that there was a particle here and that we moved the stages until our reticule was over that particle and then perform this indent. That's certainly possible. Where that comes into question is, can you image successfully on the sample to perform that kind of specified indent? If we look at, you know, so if it's too rough, that's going to be, you know, very difficult. This is 50 microns, which means that this is about 10, you know, if I was going to draw a particle on here, does it let me do it when it's, no. But you can imagine, so it should be optically resolvable depending on the sample and depending on what the composite material is. So you might be able to optically focus on it and indent from optics instead of indent from imaging. But the TS77, I think, has a guaranteed repeatability of either 10 or 15 microns. So that's something to keep in mind. Most do better. Most should be able to, but you know, I can't guarantee that it will repeatably find those composite parts. Can you smooth it? Can you make it less rough? Because that would solve the problem, but that might then impact the sputtering, right?
That's the thing. We're thinking of it as like mechanically like polish it, but because it's made of powder, once you put any extra like external force on it, it's gonna powder it up.
Yeah. Okay. So this is this goes, you know, I'm super happy to talk about this. It's much more interesting than doing fuse courts. I will say this is going a few steps beyond basic training to the point that I think I might have to get applications involved to answer these very specific questions about the graphene, see what experience they have. I don't get to test a lot of interesting things. So I think that that's what I would like to do is bring that up to my colleagues in service and then escalate it to application should I need to try and get you some better information. What you're saying, just so I have this right, you have graphene on, what's it on?
I'm sorry, graphite on copper.
Graphite on copper, and it's kind of powdery in that they are 5 to 15 micron particles. You don't want to grind it down because of that powder nature, and you imaging it might not be possible because the sample roughness is 5 to 10 microns. Is that correct?
Mm-hmm.
Okay. All right. As long as I have those details down, let me take a good review and see what information I can get to you guys.
Okay, that sounds good.
Yeah. Thank you for the details. That helps me go and get some more information.
Of course, I'm sorry that you didn't get a chance to play this interesting material.
I know it's all fused quartz and polycarbonate. I mean, my job is to get you guys set up in the world such that you can go have a great time on my instrument, know that it's working right, know that you're getting good results, and then go and like try a bunch of weird stuff on weird samples. It's just usually I'm off site before that second part happens. But yeah, I mean, we're always happy to work with you and provide whatever recommendations and instructions that we can. So let me get some people involved who have done some more interesting things and see if we can at least help you think about how to test it better.
Okay. Okay.
All right.
So
So we're still in.
So far,
I'm sorry. Go ahead.
I'm sorry. I think so far we covered like the indentation, imaging, and all left is scratch. Is that correct?
We're missing property mapping.
Oh, property mapping. Yes, that's correct.
And what's cool about property mapping is it's super fast. So I was hoping that we could finish that yet today, if you guys have time to finish up till 4, like we talked about.
Sure.
Okay. So we're gonna stay in imaging because it's more interesting to look at. Oh, sorry. But we're gonna move. Let's go back to SPM imaging. And let's move, let's see, I want to get at least 5 microns away from this indent. So let's go ahead and let's move 5 microns in X. Good. All right, and then let's make the scan size. Let's do 25 microns. Good. Okay, and then let's go ahead and engage the probe. So yeah, imaging is an interesting tool because it means that you can leave the tip over the sample and then move around, do another indent, move around and do stuff without having to wait for it to go back and forth or let the drift dissipate from all that moving back and forth increases. So sometimes for like low drift testing, we'll recommend doing testing either from imaging or from automation. Okay, so we're in contact. Let's go ahead and let's go to the property mapping tab. Yeah. So property mapping, you'll also see it referenced as XPM. And that is from our larger systems. They are capable just due to their stiffness, like the 950 when it has an upgrade or the 980, to go a little bit faster than the TS77 it can. So for your purposes, you are limited to 2 indents per second. So let's go ahead and let's make a 5, let's do a 4x4 with 5 micron spacing. So here you can see that we have our load. This should be kind of similar to methods. So here we have the loading, the holding, and the unloading. And it asks you for the number of tests and the spacing, and the number of tests and the spacing. Good. You can see it's updating live over here. And then let's do 5 micron spacing in between those indents.
5.
Good. Good. So now here we go. Gives us our preview size of about 20 microns. So how this works is that during the method, we're moving between the indents using the stage. And each indent is one of those 5-second load, 2-second hold, 5-second unload that include the motor settle time, the drift settle time, or sorry, the motor settle time, the piezo settle time, and the drift correction, right? So each of those indents takes 3 minutes apiece. And then we move on to the next one. Well, we've been working on this over the years, and what we found is that you can actually go really fast. And by going really fast, it prevents drift from really impacting the indents. And so we can actually, instead of doing it between using the stage, we can move the piezo scanner. So the thing that was in charge of imaging, that can move the transducer. So the piezo moves, transducer does the indent. Piezo moves, transducer does the indent. Piezo moves, transducer does the indent. So that's what's happening here. So it's going to do 0, 1, and as it moves between here, the stages are not moving. The piezo is what's moving. That means that your property maps are limited to the size of your piezo scanner, which can be found under system calibration scanner. Oh, your default is loaded. Let's correct that. There we go. So your max scan size is guaranteed to be 60, I think. Oh, 50 on your instrument. And here you're getting almost 94. So you got a really big scanner, which is nice. So you could make a property map that would be much larger, but we're going to start simple. There are drawbacks to doing largers or things that we have to keep, careful consideration on. So here you have 4x5, 4x4 with 5 micron spacing. The next question is the lateral move speed. That means how quickly is the piezo moving between those indents. 10 microns a second is really the fastest I would typically go. If anything, I would slow that down, but we'll leave it as the default for now. You also have the preload, which is the same as the contact threshold, which is the same as the imaging set point that we've been using, that 2 micronewtons, where it determines it's in contact with the sample surface. So we say, okay, that all sounds really good. Now there's another setting down below. Do you see the piezo translation protocol? What option do you think we should choose?
Serpentine.
Always serpentine. Here's where I really see it, right? Because if you think about a piezo scanner, especially an open loop one, 0, 1, 2, 3, if it has to come all the way back here, that's a really big move. We typically see a lot of piezo hysteresis impact that first row, if that is the way that things are set up. So yes, always serpentine. All right, so each of these is an individual indent. And just like in the method, you have a start load and an end load. Normally for property maps, people are keeping them all the same. So let's just do 5,000 and 5,000. And again, you have the option of how to vary the load. Here, we're not varying the load, so we can just leave that as is. And here you have your load time, hold time, and unload time. So here, here, and here. And you can see they add up to 0.5 seconds. So this 0.1667 is the smallest number you can have. This is the fastest this indent can go.
Okay.
You have a 2D transducer, so we might actually need to slow that down more. We'll start with these settings and see if we need to correct them.
Oh, question.
Yeah.
What's the difference of the property mapping and then the automated test? Or like, remember yesterday we leave it on to do the auto indentation. What's the two different?
The difference is the size of the automation versus the core difference is how you move between indents. So in an automation, you're moving between indents using the stages. So the tip lifts up, the stages move, and then it comes back down. Because of that, we have to do all of those extra steps. We have to do the motor settle time, the piezo settle time, and the drift because we're doing this. It also means that you can, with method automations, the grids can be as big as your sample zone. You're not limited. You're limited by the stage. You can do different methods that you can chain together. Sometimes it's just a little bit more repeatable because it's slower. It's a little bit less finicky because it's slower. For property mapping, you're moving between the indents using the piezo scanner. So it stays here. And like I said, the transducer. Piezo scanner moves indents, moves indents, moves indents. All while that stage is staying still. So because the stage stays still and we're going very fast, we don't need to do all of those extra steps. So last night we did 100 indents and it took 5 hours. Here we're doing 20 or 16 indents, and right now the total time is 17.6 seconds. So the property mapping is much faster, but you are limited then to the size of your piezo scanner.
Okay, so besides the size and the speed.
Size and the speed. Repeatability can sometimes come into question too. Some samples work better. If you have a viscoelastic sample, for example, I would not recommend doing property mapping because you might induce the viscoelastic response. If you try to make it too big, the problem with moving with a property map is that if you think about the piezo scanner, if you've noticed, I've been doing this. It is a pendulum. It's not this. It's a pendulum because it's fixed at the top. And that means if you try to do an indent way out at the outer edge, sometimes you can get kind of an angled effect too.
Okay.
Yeah. So it really depends on the sample, the purposes of the testing, what you're looking to do. Now, you want to hear where this gets really crazy?
Mm-hmm.
You can save this as a singular load function. So let's see. If I click load function settings, it saves it as a singular indent. Or it makes a singular indent. And then you could save that indent. And then all of a sudden, if you're extremely careful and set your tests up well, you can do an automation of property maps. So you could do a property map and then have the grid in the automation set up to do the property maps next to each other.
Okay.
It's hard, especially because your stages are not encoded. So yours might not line up perfectly well, unlike you might see on the 980. But it is possible that you could do many property maps overnight in an automation instead. So you can combo them, which makes the whole thing very strange.
Okay.
Okay. So if I click property map settings again, we're all set up here. You have your timing and then you have your total data acquisition rates per second. It's set to 10,000. When you try to do like a really big map, like just for the sake of this conversation, let's say you want to do a big one, you can see that your total data points exceeds what the system can hold. People are often very tempted to lower the data acquisition rate, but I'm here to tell you that doesn't make sense. If your unload segment, which is what we're fitting to, is only 0.2 seconds long, and you're taking 1,000 data points per second, that only gives you 200 data points. So you can see if you even half that to 500, you're only getting 100 data points. So your fit might then be compromised. Okay, so a couple rules for testing in property mapping. You always have to be in load control. If you remember when we talked about feedback, open loop's not going to work. It's going to be nonsense. I mean, it's going to work in that it will do indents, but they will not overlap. There will be no control. Displacement control, the feedback is too slow. It's really difficult for us to do property mapping in displacement control. So we don't guarantee it. We do not recommend it. It should be done in load control.
Okay.
The other nuance is that under system calibration on your system, there is this bias offset. Now, we talked about this a lifetime ago, it seems like, but if you recall, the transducer is a 3-plate capacitive transducer, and the center plate sits here, and we can only apply voltage to that bottom plate. What that means is I only have the ability to pull that bottom plate or that center plate down. I don't have any voltage to pull it up. What that means is that if I want to have any sort of lift, because we've seen how important the lift is to rezeroing our data, if I want to have any lift, I need to bias it forward. For property mapping, you have to bias it forward at least 1 micron, which is what it is currently set to. So you bias it forward 1 micron. And what that allows for is that in between those property map indents, when it goes to 0, it really goes to 0 volts and it lifts 1 micron above the sample surface. The idea there is that way, if your sample is tilted, you're not running the risk of like running into your sample and getting stuck.
Okay.
If you ever change the bias offset, you need to redo your indentation axis calibration.
If I change the what? Sorry.
The bias offset, you need to redo your indentation axis calibration.
Okay.
Okay, so property mapping, what's important? It's really fast. It uses the piezo scanner. You are limited to the piezo scanner size. It has to be in load control, and you have to have a 1000 nanometer bias offset. Putting all that here so that hopefully AI captures it later so that you have a nice little checklist. So whenever you're ready, you can go ahead and click start. So again, because we're in imaging, it's waiting 45 seconds for the piezo settle time before it begins the indent. And here you can see our load function, and we're following those indents. Do you see how it does this jigsaw? So it's indenting, coming back up, indenting, coming back up. This is actually your sample tilt as it's going back and forth along the sample.
Mm.
So go ahead and save this as I don't particularly, XPM is fine.
XPM?
Yeah, like, or property map, sorry.
So the load is 5,000.
5 millinewtons, yep. Good. Okay, and it automatically brings you up to the analysis tab. So in the analysis before, we only looked at the indentation axis, or sorry, we only looked at indent. Now we're in the property mapping data analysis. I'll show you where to find that here. But it's asking you for parameters. So how many segments were in our load function? And it was 3, right? Because we had the load, the hold, the unload. Your options are either 3 or 2, where you just load and unload. Segment offset. So if you recall when we looked at the load function, right, it was all this. You can add an offset at the beginning to allow for some settle time on the piezo before it begins the indentation. We did not add that, so it was 0. And then our preload, which is the same as the imaging set point, and the contact threshold was set to 2 micronewtons as we discussed. So these are good settings. You can go ahead and click OK. And it's going to take each of those indents and graph them over each other. So just for the sake of the conversation, what we're looking at here, this is data analysis. This is the indent. So this is what it looks like in our load versus displacement, right? Because it's all one data file. But our property mapping here separates it out and re-zeros it for us. So it's been re-zeroed, our data analysis is complete, and you get this property map. Now, you can imagine if you had a composite material and you did a lot of these, it would be much more interesting, but we're on fused quartz. It's fine. Here you can see which ones, this heat map always cracks me up because it makes it look so bad. We're going from 9.3 to 10.4, and really that looks like the singular outlier. So you can see here that I'm selecting individual indents, either here or if I click here, it will select all three on the hardness map, the modulus map, and in the indent. It gives me the average of the planes, so my average hardness and my average modulus. And then it also gives me the individual curves data. So this one is exceptionally high, but if I click over here, you can see that that's low. We know this one's an outlier. I know I don't like it. And so I can actually go ahead and click. Oh, I used to. Oh, there it is. Remove curve. And you can see then what it does is it averages. So it took out this individual curve and it averaged around it using the other data points. This is obviously a lot more powerful if you have a lot of data points. But here you can see now we're going from 9.76 to 9.31, which is a very reasonable spread for a hardness and this repeatability. Similarly here, 69 to 72 at worst.
Mm.
And then if we go back to SPM imaging, we're currently engaged, but not scanning. So we can go ahead and start and we can see what that image looks like. Go ahead and capture it as well.
So the capture function automatically capture when it's finished once.
Right, it will capture whatever is there when it's finished, which means that you have to start it from a good spot, right? If you were to change something in the middle of this, it would still save that image with both the half images on it. You do have a capture now button, which just takes like a JPEG of whatever is on the screen. It can be useful, for like quick data analysis or not data analysis, but like quick reference and stuff like that. I definitely don't typically use it, but. It is kind of like watching paint dry. So that's property mapping. You can do it from imaging. You can do it from, it's just nice to do it from imaging because then you get the image and the property map. And when you go to publish, you're going to have all these beautiful results in your paper that you can actually overlap and do all sorts of weird things with. But you can just do it from optics or from an automation like a regular indent as well. I just like demoing it as part of imaging because I think it looks nice together.
Okay. That looks nice.
Wonder which one, just for my curiosity, I'm going to go to property map. Nope, I'm going to go to data analysis. I'm going to reopen this. Oh, actually, I can just click analyze current file to reload it. This one was our outlier. I'm just curious if I can figure out if there's anything obviously weird about that spot. This one. Oh, it crossed through. That scratch must be deeper than I thought. So that probably caused that outlier.
Mm. Yeah.
Any questions about property mapping or imaging at this point?
No.
Okay. That's all I had for today. We can definitely open up this image and look at it together afterwards, but we have scratch left. I think that's our only thing. That's usually about 2 hours. I'll probably schedule 3 for any other questions. Did you want to meet on Friday or next week?
Next week.
Okay. What day works for you guys?
Tuesday we have off.
Oh,
Oh,
yes,
yeah.
of course. Many places do. I forget that. We don't.
Oh, I'm sorry.
It's okay. I'm more making fun of Bruker. My apologies.
Monday or Wednesday, do you have a preference?
I don't particularly. I guess Monday might be better. Would the same time work again on Monday?
Yeah.
Yeah, sorry, my apologies. I said I didn't have a preference, then I stated a preference. I would prefer Monday, but I can definitely make Wednesday work as well if that's better for you, is what I actually meant.
Monday, I think, is fine.
Okay.
It will give us some time to reflect what we learned, we've been talking about in the past 3 days. And probably we can also draft a SOP or something to send it to you to review. Maybe we can talk about it.
Yeah, we can definitely see if we can get that far. The goal of the training, or the goal of Monday, will definitely be to go over Scratch training and answer any questions you have live. And then sometimes it's just helpful to review those SOPs separately
Yes.
first, and then we can discuss if we need to. But yes, I'm here for all of that. We'll see what we can get through in 3 hours, with the primary focus being on Scratch, and then again decide if we need to go any further from there.
Okay.
I have one question before we end this.
Yeah.
Like, we have the restriction of the XY coordinates for the property mapping.
Yes.
What format is it saved, this property mapping?
I think it's still a .hys file, because it does
Okay.
treat it as a singular indent file.
So we can recall it when we want to see that or visualize that or map that property, right?
Yep, absolutely. Sorry, I was just trying to make this interesting. So if you go to, yeah, there it is. So in property mapping, you can, nope, sorry, in data analysis property mapping, which is the screen we're currently in, you can go to File, select File for analysis, just like we do for, looks like you guys had a couple other ones in here. I have no idea what these are, but they're from when the installation happened, or maybe from practice afterwards.
Yeah, those are practice we tried earlier.
Yeah, it
So
looks
my
like that one
question was
didn't go
like,
well.
my question was like, if we feed that 10 by 10 grid, will it able to plot that?
So this is where it plots it. This is the information. It does plot it here as well. 10 by 10 grid.
Mhm.
No, it does not. It has to be a property map to be plotted in the property map analysis. Is that the question?
Yeah, because we are picking up the .hys format, right?
Right. So what I mean is that during the automation, you get one HYS for every indent. During
Okay.
property mapping, you get one HYS file. That's it. This is it.
Okay.
This is your .hys file. And then the system has this specialty, proprietary analysis function in the property mapping to take that singular .hys file and break it apart into these maps.
Okay. Okay. I got it. Thank you.
Okay. That being said, the .hys files, like for an individual indent, actually, I'm sure that there'd be a way to figure out how to do that in the post analysis if you're clever with, coding between the data that's in each .hys file, if you wanted to do it for an automated result.
We'll work on it and resell it back to Booker.
Okay. Sounds good. I need more help.
Okay.
Yep. So just before you leave today, make sure you get back away from imaging. You don't want to leave it just imaging and, for a long time.
Let me disengage it right now.
Yeah, either disengage or retract depending on what you want to do with it later. But yeah, good. Yeah, I try. My rule is I never leave the tip in contact when I walk away.
Yes. So that's why earlier you see we did some mapping. That's why, if you recall, the first day I asked, okay, why does it keep like going? I thought when it's like finished, it should like disengage itself or give a cue say it's finished or something. And also, if you remember, for this one, we use the BG subscription or something, because at the beginning it's all white.
Yep.
is out wide and it was going a couple of times, there will be something on it. I said, oh, maybe you should, go like 2 or 3 times to capture but it shouldn't, it doesn't really make sense to me earlier, like why you're doing like that.
Mm-hmm. Yep. Well, that's the purposes of training, right? Is to make sure that we understand how to look at it and how to ask it to do what we need it to do.
Yes.
Okay.
Very good.
Okay, I will send another meeting update. Your homework is to try to make another tip area function out of that raw data.
Yes.
Good.
You'll
Okay.
get that done before the meeting.
Sounds good.
One more question from that tip area function. In that tip area function, there was one outlier.
Mm-hmm.
Do we remove that and then do the tip area function?
It would have been better if we had done that. I guess I just left it in there because it was there and it was only one. If you have more than one, definitely. I generally make like an outliers folder and then move them in there. Because we had one on 200, it didn't seem urgent and it didn't really impact our results at all. It didn't change the fit, if you recall. If it would have come up and like done this, or if we had only done 10 indents, then absolutely I would have pulled that one out, right? Because that's a 10% error. But in this particular case, it wasn't super important.
Okay. Okay. So actually, let me just withdraw it because the analysis does not need for the tip to contact the sample. So I'm just going to put it back and do that.
Okay.
All right. Thank you so much, Laura. I appreciate you.
You're welcome, guys. It's wonderful to work with you. I will have a great rest of your week. Someone talk to you, and I'll talk to you on Monday.
Too. All right. Thank you so much.
Thanks. Bye.
Take care. Bye.